Hi, I'm Xuan, and along with my two group mates, Sumesh and Nathaniel, we have embarked on a project to predict bankruptcy using machine learning. First, let me introduce the problem at hand. Since 2000, more than 745,000 businesses have filed for bankruptcy in the US. Bankruptcy can result in significant financial losses for entities, and being able to predict bankruptcy can help entities pinpoint their problems and cut their losses. However, the abundance of financial data can pose a challenge in determining which factors to prioritize when forecasting the likelihood of a company's bankruptcy. Upon finding a suitable bankruptcy dataset, we thus decided to investigate the performance of machine learning models and the effects of various variables in predicting bankruptcy. With this approach, we aim to answer our overarching problem of what is the optimum machine learning model to predict the likelihood of a company going bankrupt, and are there specific variables that can better determine bankruptcy? Now, our bankruptcy dataset is from the Taiwan Economic Journal with data from 1999 to 2009, and it was obtained from Kaggle. We decided to utilize this dataset as we hypothesized that we could identify the best machine learning model using financial data from this dataset. Given the nature of the dataset, we decided to compare three machine learning models, namely the support vector machine, decision tree, and neural network models. To identify specific variables that could potentially better predict bankruptcy, we then expanded our investigation to see if our models would perform better if we narrowed down the number of metrics or variables used to predict bankruptcy from 95 to 10.
During our data analysis and exploration phase, we utilized four main libraries to assist us: Kira, Seaborn, Pandas, and Scikit-learn. These libraries provided us with a range of tools from data visualization to machine learning algorithms. To form our main dataset, we utilized Kaggle. The dataset we obtained was highly relevant, well-structured, and challenging, making it an ideal resource for data cleaning, analysis, and machine learning. With up to 95 columns of statistics collected, we were able to paint a comprehensive picture of the company we were analyzing. Cleaning our dataset was a crucial step. To address this, we implemented data imputation, which successfully identified and removed any missing or null values from our dataset. When building a model, having too many variables can negatively impact its performance. To address this issue, we engaged in dimension reduction to eliminate any irrelevant data from our dataset. To identify which variables to eliminate, we considered the correlation between various data points against the bankrupt variable. In this case, we reduced the number of columns from 95 to the top 10 most correlated columns. We then utilized scatter plots to identify any potential errors or anomalies in the data. We observe a strong negative correlation between net worth assets and debt ratio, and that these two variables do not significantly influence the rest. We also use Violin plots and bar chart to explore the relationship between non-bankrupt and bankrupt companies. Our analysis showed that there were no significant difference between the two data sets, except that the variables in bankrupt are a little more spread out. This may be due to the fact that the dataset was highly imbalanced, with a much larger proportion of non-bankrupt companies in the dataset. We then explore our best indicator, net income to total assets, where we notice outliers congested at the first and third interquartile range. Therefore, we were engaged in the removal of the outliers. Outliers were identified using net income to total assets as our data point, and rows corresponding to it were removed. During our analysis of the outliers, we made a major insight. 16% of the bankrupt companies in our dataset were concentrated within just 8.23% of the outliers. This finding was alarming, and we realized that removing the outliers will lead to a loss of information and potential biasness in our analysis. Additionally, we could overlook important factors that could have a significant impact on predicting bankruptcy. Therefore, we decided to keep the outliers in our analysis and take them into consideration when building our model. Thus, we need to engage in upsampling to help balance the data. We utilize a method called random upsampling, which involves making copies of the minority class. This resulted in a dataset with an equal number of bankrupt and non-bankrupt entries. By doing so, we were able to improve the performance of our model and reduce the impact of class imbalance in our analysis. Comparison of our old and new dataset showed no major changes in the underlying relationships between features and target variable, indicating that our upsampling method was effective in maintaining the integrity of the data.
Now, let us take a look at the three machine learning models we'll be employing to predict bankruptcy on our dataset. The first model we'll be using is a support vector machine model. The SVM model works by finding a hyperplane in n-dimensional space that can distinctly classify the data points inside our dataset. In this case, the two hyperplanes will be the n equals 95 space for all variables and n equals 10 space for the top 10 variables. The second model we'll be using is a decision tree model, which recursively partitions the dataset based on the values of the variables present. Lastly, we'll be using a neural network that consists of a large number of interconnected processing nodes that work together to process input data. In our implementation of the SVM model, we first created dummy variables for categorical features to prevent multi-collinearity. This refers to the high correlation between two or more variables in the dataset, which can cause problems when our model interprets the data, as it can make it difficult to determine which predictors are truly important and which ones are redundant. Numerical features were also scaled to ensure they have zero mean and unit variance, ensuring that all features have a similar impact on the SVM model. Upon comparing the models based on the AUC metric or area under curve metric derived from the receiver operating characteristic curve, which plots the model's true positive rate against the false positive rate, we can see that the dataset with all variables had a higher AUC as compared to that of the top 10 variables. It also had a higher accuracy. This implies that the model can distinguish positive and negative classes better on the dataset consisting of all variables and is more accurate as well. The next model we'll be looking at is the decision tree model. While implementing this model, extra steps were taken to ensure overfitting of the model does not occur. This was done by pruning the tree, which meant unnecessary branches and leaves were removed from the node that did not contribute to an increase in the model's accuracy. Upon comparing the models based on the AUC derived from the ROC curve, we can see that the dataset with all variables had a higher AUC as compared to that of the top 10 variables. It also had a higher accuracy. This implies that the decision tree model can distinguish positive and negative classes better on the dataset consisting of all variables and is more accurate as well. The last model we'll look at is the neural network model, which comprises 128 neurons in its first layer, 64 neurons in the second layer, and 32 neurons in the third layer. The output layer is a single neuron with a sigmoid function, which is used for binary classification problems. To prevent overfitting, batch normalization and dropout was used. Lastly, the model was optimized by using the binary cross entropy loss function. Upon comparing the models based on the AUC derived from the ROC curve, we can see that the dataset with all variables had a higher AUC as compared to that of the top 10 variables. It also had a higher accuracy. This implies that the neural network model can distinguish positive and negative classes better on the dataset consisting of all variables and is more accurate as well. When comparing the 6 different ROC curves in one plot, we can see that the top 2 models are the decision tree model and the neural network model. Furthermore, the dataset with all variables performed better on the AUC and accuracy metrics across all models. The neural network model came out on top in terms of the AUC metric with a score of 0.9869, while the decision tree model had the highest accuracy of 96.63%.
After comparing machine learning models, we can conclude that models trained using the full dataset perform better than those trained with only the top 10 variables. This suggests that factors affecting bankruptcy are not just limited to the top 10 correlated variables, and businesses need to consider all aspects of their operations to identify potential bankruptcy risks. In our analysis, we found that the decision tree and neural network models were the top 2 performing models based on accuracy and area under curve respectively. The decision tree can correctly classify a maximum number of firms, while the neural network is better at distinguishing between bankrupt and non-bankrupt firms. However, the cost of classifying a bankrupt firm as non-bankrupt is more significant than classifying a non-bankrupt firm as bankrupt. Therefore, entities which tend to be more risk-averse should use the neural network model as it has a higher sensitivity and area under curve. Through this project, we used several technologies that were not taught in the course itself to ensure a holistic and proper evaluation of our dataset. This included upsampling of our data, using neural network models and support vector machines for data classification and prediction, and utilizing the receiver operating characteristic, also known as ROC, and its area under curve to compare and evaluate the performance of machine learning models. One of the essential things we learned in this project is that using a raw dataset can lead to skewed results, hence the need for appropriate sampling techniques such as upsampling. Furthermore, accuracy is not the only metric to determine the success of a model. We should also consider other metrics such as the area under the curve of the ROC graph. Additionally, context and intent are critical in arriving at conclusions. For example, though we concluded that the neural network model is the optimum model, if the entity in question is not risk-averse and will prefer a model that gives fewer errors overall, they will prefer to use the decision tree model. For further exploration, we intend to expand our data to validate the model and investigate whether including sector-specific data could improve performance. In conclusion, our analysis shows that the neural network model is optimal to predict the likelihood of a company going bankrupt. There is no specific variable that can better determine bankruptcy, so entities should consider all aspects of their businesses. With our analysis, we hope that financial entities are empowered to make the best decision for themselves and their customers. Thank you.